Most of our analyses up to this point assume that the entire abutment acts as a single block sliding uphill or downhill, depending on the site. This allows us to use sidewall friction and include the tier and tower weight in our sliding resistance checks, not just the weight of the anchor, significantly increasing the capacity of our bridge abutments. However, there is a missing link we need to check. In order to make this assumption, we are assuming that the ramp walls act as compression struts between the anchor and foundation, supported laterally by the interior fill on one side for the full height of the wall, and by native soil on the other side for the embedded portion of the ramp wall. The wall transfers a portion of this force into the foundation and tiers and towers. So we'll check them for bearing, shear, buckling, combined axial and flexural forces, and flexural tension. All of these checks come from ACI 530-13, also known as TMS 402, the Masonry Society, and MSJC Masonry Standards Joint Committee. We'll look into Chapter 8 for allowable stress design of masonry. And specifically, we are interested in Section 8.2 for unreinforced masonry. However, before we dive into the code, let's first define the loading on the walls. Force flows from the cables into the gravity anchor beam. So when someone steps on the walkway, the suspenders will transfer this evenly between the walkway and handrail cables, and we'll get the force in the cables that travels all the way here into this anchor beam, which then in turn bears on the ramp walls. To transfer that force all the way back into the foundation and tiers. And according to ACI 530, this load can be dispersed at a 2-to-1 slope in running bond masonry until meeting at an edge or half height, whichever is first. So this allows us to disperse our load, like I've drawn here, along the entire wall width and entire wall height, which will always be less than half the wall height. So unlike a freestanding masonry wall or column, force will be dissipated into the ground via friction to resist the load. This is ignored in our analyses. I've shown it here. And we're going to check the design based on this max force transfer point of the wall. So we'll assume all of the force is transferred at this max force transfer point, even though in reality we're going to experience some dissipation of that force into the ground via friction, and ideally by the time we get to the front of foundation we have zero force because all of that force has been dissipated into the ground via sliding.